Okay. Hello, everybody. Good morning. Can everybody hear me? Yep. Okay. Good. So, I'm Andrea Barisani, giving a presentation about practical exploitation of embedded systems. I've done this work with my colleague Daniele Bianco, who is unfortunately not here. So I work for InversePath, a company which I founded, which does, usual things, security testing, but we focus on both software and hardware at the same time, and we have to deal with a lot of exotic systems. And I like this presentation because it's a good chance to talk to you about some very, very specific, interesting challenges that we encountered in the past years, and that we think are, have some value either from an historical perspective or and also a practical perspective. So I hope you will enjoy the unique challenges that I'm going to present. So embedded system. So when we talk about an embedded system, we usually refer to a system which is designed for a very specific function within a larger system. So it is embedded as part of a complete device. And devices that fall under this category you can refer to an embedded system of what controls a router on the boards that control your printers, which, sometimes they have a Linux system or they have a real-time operating systems, point-of-sale devices, which might have their own custom operating system or firmware, or sometimes they also have things like Linux, which are more common, smart cards, automotive equipment, avionics, and these are all kind of things that we deal with during, for work, and that they always pose interesting challenges. But you also have embedded systems within your own laptops, for instance. So some controllers, you have lots of controllers in your hardware that they can be classified as embedded system, like the LAN controller, the chip which runs your wireless car is an embedded system. Sometimes a quite powerful embedded system. The system management controller, which we're gonna use an example at the end of the presentation, and so on. And again, operating system, you can have standard systems that everybody knows, or you can have things which are a bit more exotic, like the Xworks, ThreadX, Lynx OS, Pike OS, and so on. And exploitation of these devices in the past years has been a really, really hot topic. For many reasons. So I just want to cover some very specific issues that we think are really relevant and interesting when dealing with these kind of devices. So before getting into details, of course, the first thing that pops up when you have to deal with this kind of system, usually you have to gain knowledge about the system that you're targeting, which means that you have to find some kind of debugging access to either, debug what the CPU is doing, or, try to dump the memory and so on. And, and the most available debugging or access interface, you can have serial interfaces on many devices or JTAG ports. And some of them can be found, really, really, really easily, and some of them are, they're a bit more difficult to find, especially the JTAG ones. So serial interfaces, even if you're not into hardware hacking at all, it's very trivial to find them. You can buy a logical analyzer, very cheap, and usually you can find, by just looking at the PCB, you can find the series of pins that can be associated to a serial interface. Of course, if you are lucky, the PCB board will tell you that it's a serial interface. If you're not, you can just probe them around, and it's often very, very easy to find. Of course, the form factor will not be a normal, connector. It might be something completely different, but usually they're, you have the pins in a straight line, and they're very easy to find. And in order to find one, you can start intercepting TTL levels. You reboot the device and you wait for data which should come out from what are the TX, the TX and reception pins. And the protocol parameters usually are always standard. So, this is an example of a logic analyzer attached to a board, very crudely, it's not too refined. And with the software that comes with your logic analyzer, you can find, and most of the times you can also decode on the fly what's there. So it's super easy. JTAG, on the other hand, it's a bit more complicated because, despite being a standard, the standard doesn't tell us too much about how things should be implemented. And JTAG is really powerful. It allows you to do in-circuit debugging, and you can step the CPU, you can do breakpoints, you can have full memory read-write access, and sometimes it's really critical to get JTAG access in case, for instance, you have a system which deals with an encrypted firmware, and you don't know where your encryption key lies within the system, but you do have JTAG access, or you were able to find it, that might be really, really useful in exposing the key, or and to have access to the system. But the problem is that, so while the interface is fairly easy because you have data in, data out, you have a clock, mode select, and then the reset pins, some vendors, or at least in many systems we found, they implement, they have two levels of protections. The first level of protection is that from an electrical perspective, things are not soldered and are not set up in a way that allows you to have JTAG access. So sometimes you have to remove a fuse, or you have to solder a bridge to add some resistor in order to have the circuit compliant to what you need to do. And this is, of course, not documented if you're dealing with, some remote, some avionic system which you know nothing about and you need to exploit. And this is one problem. But, usually you can work around it, and, by probing very carefully, you can understand where the actual pins are. So, for instance, ground and VCC, the voltages are really easy to find because you can try to pull them down and pull them up, and if something will not pull down, then that's VCC, and if your connection will not pull up, then it's going to be the ground connection. So, by doing electrical probing, you can find the different pins that you're looking for. But once you found them, so usually if you would follow the standard, there are some different scanning strategies that you can apply to understand which pins do what. And for instance, the standard says that after you reset that device, it should always be either in bypass mode or ID code mode, which means that depending on the case, you can send some data on what you think is the data input, and then after one clock cycle, you can get some data out of the data output, which is either the same thing that you're sending on the data input in case of bypass, or it will be the ID code in case after reset you go into ID code. But the problem is that, at least in our experience, we have encountered many devices where the standard was not being honored because there was a custom initialization device that you really have to know in order to put the system in a state that allows you to work on. And sometimes it's really extremely difficult to probe for this initialization sequence without either damaging your equipment, or if you don't have a reference that you can use and you can maybe intercept, like a custom debugger hardware which is given to you by the manufacturer and that you can piggyback on to see what's going on, it becomes really, really difficult. So there are some interesting challenges when doing this, and there are a couple of projects that you can find online where they help you in finding and scanning the JTAG pins when you think you identify them. They're not as complete and as efficient as we would like them to be, but they're a very, very good starting point. And you can easily modify them to obtain what you want and to implement your custom initialization sequence in them. And usually microcontrollers are a great tool for playing with this kind of access and implementing your own scanning techniques. So other than JTAG, and if you're not dealing with a system where you have heavy encryption on the memories, of course the easiest thing is to actually desolder, to identify the memory and desolder different flash memories that are available. And these are either, 100% of the times they are, either SPI devices or I2C devices. And you physically obtain direct access to them by desoldering them and actually connecting your memory reader, like you can have FTDI-based readers like this one, or this is an SPI reader which conveniently then allows you access over Ethernet, which you think it's really nice. So you can use these kind of converters, and you manually connect your chip on them, and you get access to the chip. And you know, it's very, very easy. You know, it's not, if you can desolder the memory, it's fairly easy. And most of the times you will always have test points on the board that will allow you to read the memory without actually having to desolder it. You know, so look for them before trying to desolder the memory. So, of course, sometimes you might not get access to the memory for whatever reason, or you get access to the memory, and there's one very critical thing that you need to understand if you want to modify the contents of the memory without triggering any, I'm not saying security, but integrity verification mechanism. And you know, and the first thing that pops up is reverse engineering the checksum algorithm of the images that you have. And if you do that, then you can either use collisions in order to create your own custom firmware that will have exactly the same checksum, or you can modify the firmware along with the checksum. We always favor the collision approach, because there have been cases where we thought that the checksum was being located for verification purposes in one specific location, and in some systems the checksum was actually included twice in other memories and other systems. And you risk breaking your system if you upload a firmware which doesn't match both checksums. So by using collisions, you are, you know, since you're creating or modifying an image with exactly the same checksum, then you're good to go and you don't have to worry about that. And since creating collisions is very easy, you need just 4 bytes that you can arbitrarily manipulate within the firmware image. So if you have that freedom, which is, you know, you always have that, then, you know, just do a collision and you will be, you know, much safe to do. Now, you might think, and most people think, that, you know, CRC algorithms, okay, you have a few of them, but you know, that is a very standard thing. But in our experience, this is one of the, you know, cool things that I'd like to talk about, is that is not always the case, and you need, you know, to dig in a little deeper to understand what's going on. So of course, CRC42 is the most common algorithm. You know, it's undocumented. It has a polynomial which is used for the computation of the algorithm. Which, however, we got to be careful if you want to find that polynomial in maybe the firmware code that you extracted. You will always have to check for its reverse representation. So even if you have documentation that says that the polynomial is 4C11DB7, you have to actually look for EDB8832. So if you, whatever firmware that you might have that you have disassembled, if you search for that value and you find it in the firmware, then it's a, you know, extremely good indication that the firmware is either checking CRC42 for its own sake, or is computing CRC42 maybe for sending packets out or for, you know, some integrity. But, you know, that's one of the first values that you go and you look for. However, most of the times you don't have a straightforward CRC42 implementation in the firmware. And there's one very convenient model which is called RockSoft, which defines different parameters that can be tuned and used with the same algorithm in order to have basically, you know, different checksum with different polynomials. The result will be different. But knowing that there is this existing model allows you to brute force your way through just by changing those parameters and not worrying too much about having to implement a completely different algorithms. And the RockSoft model is very convenient. So you define, you have the width of the value, you have the polynomial, then you have an initialization value. You have parameters which tells you how the bits should be handled, and you have a XOR out value that is, you know, that is used in the final register at the end. And when you have specification about the RockSoft model, you always have a check word, which is the checksum value obtained by, you know, by using 1, 2, 3, 4, 5, 6, 7, 8, 9 as an input, and then this is the value that you can check to see if the algorithm is matching what you have. So, and by just playing with these parameters, you can easily find if you're dealing with CRC16, 32 POSIX or CRC42, the standard one, or something a little more exotic like GEM CRC, which has the same polynomial, but it has different parameters in the XOR out and in the way it handles the least or most significant bits. So just by knowing this, knowing that there is this construct for assessing the different checksums, you can find GEM CRC very, very easily. And this is helpful when you have code that maybe has some comments which says that it's using CRC42, but then nothing works because it doesn't match your expectations, and then you find that it's actually GEM CRC. So by knowing this model, this is really convenient. And also you can easily find, if you have the firmware image, the assembly representation of the CRC algorithms like this one. And you can either have an algorithm which uses a table, so a pre-computed table of values or not, and also identifying the table, and each of these algorithms will have their own table that you can easily compute with this code. If you search for the table within the code, that will give you a precise indication that the algorithm is being used. And I just left these for reference here in the slides. We're not going to comment them too much at this stage. However, what I want to say, and the very interesting thing, is that sometimes you might have algorithms that are checksum algorithms very similar to CRC42, but no matter how much you play with the Rocksoft model, you will not find them. And that's something that in the past it drove us crazy, and that's why we think it's useful to present this, because it might save other people times. And also from an historical perspective, it's pretty interesting to know that there are different algorithms depending on the POSIX specification draft version that it is being applied. And again, we're not talking about a CRC algorithm which has different Rocksoft model values. We're talking about an algorithm which has specific exceptions, which makes everything different. So for instance, the draft 11 version of the algorithm has an exception here. So the table, when you generate the table, the very first value is different. Is not computed in the same fashion as all the other values. And that, of course, changes everything. And as long, you can play with the parameters as much as you want, but it won't make a difference. And the second difference is when you actually do the algorithm, it doesn't matter if you use the table or not, you have an exception that when this index is 0, so if you have an intermediate 0 during the algorithm, then you have a reminder value that you keep that is just being shifted on and on. And this is, this is a major difference that makes everything different. And this is not the only case where this happens. So here, for reference, we have the same algorithm without using the table. And we can see that we have a polynomial which reflects the standard CRC42. So you might find that in the code, and you might say, oh, well, the standard CRC42, so I might as well use that. You do, and then you break your device. And that's very, very unfortunate. And there are other drafts, so it's very funny, actually. At least, I'm fascinated by these things. Maybe call me a nerd, maybe I'm weird, but it really fascinates me that you have draft 9, draft 11, and draft 12 of the POSIX specifications, and they all do not follow the Rocksoft model, and do all lead to separate check words. So they're all different implementations. And if you look at the draft, actually, you will not find any difference in the text. It will not say what are the differences. You actually have to check into the historical implementation that was designed at that time and that refer to that specific draft. So, and there are a few reference code that are around that some people sometimes pick up, and they think that's the standard CRC42 implementation. And we found all of these different flavors while analyzing devices. While on the other end, if you have the standard POSIX algorithm or the PKZip, the Ethernet, sorry, the CRC42 flavor, which is used for things like the Ethernet checksum and so on, it also falls under the Rocksoft model, and so that's easier. But this is just to show the difference between the different versions. And if you happen to have QNX, a QNX box, the QNX user space checksum tools is one of the most complete ones in actually applying the different drafts. I don't think it has all of them, but it has most of them, and it's the only documented user space tool that does that. And I think that's pretty nice. So this is one challenge that you have to deal with. Once you deal with this, you can arbitrarily modify your firmware, and you can start playing with it. And we thought, we think this is a really interesting characteristic of the algorithm, which is really worth mentioning. The other thing I want to talk about in relation to embedded system is runtime kernel patching, which is a topic which has been discussed for a long time, normal operating system, but that is very useful to do. It's very convenient where you're dealing with real-time OSes. And the reason why this is useful is because in many cases we have been in a situation where we cannot extract the information we needed from the hardware because either we didn't know where it was or it was too expensive, it required too much effort to actually do. But we knew that the OS was actually accessing the values that we were looking for. And one of the prime examples is if you have a cryptographic key, which the operating system is actually using at some point. And that is stored somewhere on hardware, which is either tamper-proof or that is really hard to identify and access. And there's a habit of most embedded systems to, even if they have a full-blown real-time OS that has the concept of kernel space and user space, to do everything in kernel space and have drivers in kernel space that pretty much they do everything. So you might have a device which exposes to you a web server. It has a real-time OS, and you might think, oh, that's going to be a user space process, and in reality is the actual driver in the kernel space that it's doing it, which also leads to interesting exploitation possibilities when you know that your web server is running on kernel space. So anyway, so runtime kernel patching, so on this kind of operating system, you don't have all the full-blown protections that nowadays you have on modern systems. So it's kind of going back to the old days when you can just open devmem and then seek to the pointer of the function that you want to overwrite, and you put your new pointer, and then in your new function that you can do your inspection or your interception of the data that you need. And there's one interesting thing which most people, they do not realize this, is that in order to do this, in order to create binaries and create code that will run on the target system, you don't need to have the specific OS development toolkit for that target system, which is available in some cases, but you don't need to do that. You can create binaries. You can use C as a user interface to assembly in a way that you don't have to include any header, nothing else, and as long as you can find the symbol table on the system which tells you where the functions are, and now we're going to see an example about that, then you're pretty much set. So this is an example of doing a function hijack for arguments debugging. So suppose you want to identify, or you think you have identified a function which at some point is handling a cryptographic key, and you want to know what that cryptographic key is. So you need to debug the arguments which are being passed to a specific function. So you have a pointer of a function which you think it takes as an argument a cryptographic key, and you want to debug the arguments which are being used without affecting the process. You don't want to disrupt the operation of the system. You want to silently include your code, get all the different arguments, and you don't know how many they are, and then have the code go through. And in order to do it, so this is how you do it. So you have to do two things. You have to replace the pointer of the original function with something that directs to your own wrapper. You have to copy the original function in a placeholder value, then you do your own thing, and then you jump back to the original function. So in order to do this, first of all, and this is the only thing in this code which is dependent on the specific architecture that you're analyzing, you need to find the opcodes for the jump that you need to do. So in this case, this was a MIPS. So if you have your wrapper pointer, because so function wrapper, this is the function that we have later here that is will actually be the wrapping function for your custom code. So if you cast that to an int, then you automatically have the pointer to your function. So, and function pointer is the argument of this whole thing, which is the original function. So you take the datasheet of the instruction set for your specific architecture, and you find the math that allows you to create a jump instruction, that redirects to your own function. And sometimes you have relative jumps, and that's why you need to do the math. You cannot have absolute jumps. And this is a simple map. So then you need a function placeholder, which means for the original function, which means that you need to know the size of the original function that you're dealing with. And most of the times you don't know the size of the original function, but you can overshoot. You can allocate memory which you think is big enough to contain in that function. If the problem is if you allocate a placeholder which is smaller than what you require, but if you have a bigger placeholder, then it's no problem at all. If you copy more data, it's no problem. And then you can define a prototype for the placeholder value. And we can see that is in prototype, we define two arguments, A0 and A1. But you don't need to know the exact number of arguments of the original function in order to do this. If the original function has 15 arguments and you're just defining 2, it will work. If the original function has 2 arguments and you define A0 to A15, it will still work. Because the way the arguments are pulled and pushed from the stack in most architecture, it means that by even overshooting the number of arguments that you're putting in your placeholder, it will not affect the code. And this is critical. It means that you can really inspect how many arguments the function is getting without affecting its operation. And then you have to find where memcopy is. So you need to know what's the value for the pointer to memcopy, which is really easy. If you have access to the system, you can see the libraries and so on. You copy the existing function in the placeholder. You replace the original function pointer with your own jump that we defined before, and then with an op in this case, because in this architecture you always need an op after the jump, and then you have your function wrapper. So the function wrapper right now is not doing anything, it's just calling back the original function, but here, in this area, you can put your custom code, which is maybe printing the arguments, it's saving them because you know the system calls for write and open on a file, anything that you might do. And as long as you don't modify the data flow and you're not modifying the arguments, you can debug them very easily, very silently, with no overhead, and the system will go. And with this way, we found many pieces of critical information like cryptographic keys that we needed to access, and that it was simply too expensive and too demanding to actually do it by identifying where the key was in the hardware. And it might sound difficult, but it's actually straightforward to do, and it's really, really effective. And again, you don't need to know too many details about the original function. You just need to have a hint of which pointer you might look for, and you don't need to have the development toolkit for that specific environment. In order to understand the different system calls, there's one very effective technique that applies to most real-time OSes, is that if you can find in memory the system call table, which is usually very easy to find because it's a sequence of pointers which are very close to each other, and so it's a very big table, and it's usually easy to find. And the order of the pointers in this table will tell you what the functions are, because they will either be compliant to Linux-based systems or to BSD-based systems. So in Linux system, you have a specific order of system calls, so you have system call 0 is open, system call 1 is write. That might not be the case, just for giving you an example. And on BSD, that order is different. And we found out that every single real-time OS system that we analyzed was compliant to either Linux or BSD. Not necessarily consistently with what the vendor would advertise the system as being compliant with. So you might have systems which are advertised or are BSD-like system that will have a system call table which actually follows the Linux numeric ordering and so on. But one of the two is usually a very, very good starting point. So, any questions so far? Okay. So, having covered all of this, I want to give you a practical example of how to hack into an embedded system which is included in, in this case, in every Apple laptop, which is the Apple System Management Controller. So it's an internal embedded subsystem which is only on Intel-based Apple laptops, but it can be found in other laptops like ThinkPad laptops. They also have an extremely similar system management controller, which is also used as keyboard controllers on ThinkPad laptops. And this system, it is interesting from an educational perspective, we think, because it's something that most people are not aware of, that it can be flashed, and the properties of the update mechanism suggest that there is some security involved, and it's an interesting process to reverse engineer that to actually understand what's going on. And it's one chip on your laptop where you can persistently upload firmware on it. So it's a good target. So what is it used for? It's used for many things, more importantly for thermal management. So it monitors the power and it manages the battery. It can use as a flash bridge for storing values. So there are some values in the BIOS which are actually stored through the Apple SMC that provides a bridge to an SPI flash memory. It provides the ACPI OS interface. It provides some utility functions like buffering signals and shifting the levels of the signals. So it is used for converting some voltage levels by other components on the board that need to do that. And it has custom and programmable functionality. So an Apple system, it manages the power button activity. So every time you press the power button and the system shuts down is because the Apple SMC is instructed to do so. And on one side, it controls the power button, and on the other side, it can control, it can do power management on the system. The same thing goes when you open and close the display lid. It is also attached to the side of motion sensor, so it can get information about the motion sensor and decide to spin down the hard drive if it thinks that your laptop is, falling from 2 meters and so on. Checks the ambient light, it controls the keyboard light and other indication lights. So, it has a relatively powerful role into your laptop. And it's also interesting that there's a defined interface between the Apple SMC as the OS. So user space has actually means of talking to the SMC and getting data back and forth. So every time you install a tool on macOS or you use existing macOS tools that will tell you exactly the RPM of your fans, for instance, that is being performed by querying the so-called SMC keys. So the interface is that you query a specific key and the SMC will give you back the value of that specific key. And also one thing, you have the Ninja action timer, which I think is pretty cool. So any microcontroller has something which is called the Ninja action timer. I think it's worth investigating. And these are, an example of the different keys that you can get. So the RPM for fan 0, you can access the ambient light sensor temperature. You can have how many, what's the brightness of the light that is being detected. You can have the current of the CPU, and you have the motion sensor and so on. So this is what's just one example. So how do you approach, hacking the SMC? Where do you start from? So the first thing, you go and check if Apple does firmware updates on it, and they do. So it's really straightforward. You get the DMG file, the Apple disk image from Apple. you easily understand that this is a gzip compressed CPU. So I'm doing all of this on Linux, right? Because I don't want to do it on Mac OS X for whatever reason. So this is just to explain how the format works. So you decompress it and use CPU to access the files. And the interesting files within the archive, you have an EFI binary. So EFI is a standard which is replacing the legacy BIOS implementation, and it's a big pre-boot environment. So when you have an EFI binary, it's a binary that can be executed as soon as your operating system starts without having the OS being booted up. And then you have these two SMC files, which indicate that they contain the firmware. So the EFI binary is a universal binary, works on 32 or 64-bit. And there's a utility on Apple which is called bless, which can be used to tell to the system that the next boot, it should actually boot that binary. And this is how they perform the firmware update. You install the firmware update, the system blesses the SMC flasher EFI, you reboot the system, and that binary is executed in the pre-boot and perform the firmware updates. And it gets, as an argument, one of the two SMC files, which they do actually contain the firmware image. And these files are checked for integrity. So let's see how integrity is being checked. So this is what the file looks like. So this area here I just cut for brevity. So you have a letter which supposedly gives you an indication of what this specific row represents. Then you have a number, you have data, and then you have another value. So the first thing that you see is that here you have 64 bytes of data, and here you have 64. Here you have 20 bytes, and here you have 20. So that information is length. And what H, S, and D means, so H is hash data, S stands for security data, and D is an actual data block. And this, the first thing that comes to mind, which turns out to be the correct answer, is the memory offset of the firmware which is being flashed on your device. So we have the length, we have the data. So we basically need to understand what this area here and what kind of checksum is being used here, because this is some kind of check word which presumably is used at the end to validate the integrity of the row, which is something that many other formats do. Like you have the SREC format, which is kind of similar to this one, but this is not 100% compliant to that. There are some major differences. And the memory address. So by analyzing what resembles to be the Intel Hex SREC file format, you can actually find out that the checksum algorithm is, something extremely simple. So the word that you see at the end of the file is actually the sum of all the different values that are contained in the row, and you just take the least significant byte and you put it there. So, this is very trivial to compute. And the security block is none other than the sum of all the previous check words for the hash data. And it's the same thing goes for the data block. Each row has its own checksum, and then at the end of the block you have the sum of the checksum. So you do a checksum for each row, and then you sum all of them. And this is how they do redundant integrity checking. So once you realize this, so this, this is after explaining all the subtleties of different CRC32 draft versions, I'm showing you a much more simple example. Which, however, you gotta figure this out, because if you overthink it and you think it's something more complicated than that, you will never realize it. So sometimes, you have to assume that they're doing something really stupid, like in this case. So once you know all of this, it becomes trivial to modify the firmware image. And it's also very convenient, because if you know your modify one specific value, you just need to subtract the previous value and then add your own, and you automatically have the checksum for that specific row. So it becomes really, really easily. So once you know that you can modify the firmware, you know, as you please, you got to understand what is going to be the architecture of this chip, because otherwise you cannot write relevant code for it. So what do we know? The first thing that you know is that the first relevant data block in the data, assuming that this is the address in memory where you're going to flash your firmware, is this value here. And so that gives you one piece of information that you can try and look in different data sheets for different chips, because, you know, every single architecture, every single chip will tell you that, oh, the executable memory will start from this address, and that might be one good indication. The other thing that you know is that by witnessing lots of zeros in the code, you might think that's a NOP operation. So you know that NOP is going to be 0, 0, and that might also give you an indication of what the architecture is. And then, of course, if you have enough money or enough, you know, enough budget effort to actually dismantle your laptop, you can also visually see what the SMC is, or you can go on iFixit, and then iFixit will do it for you, which is really, really convenient. So we thought that this is the SMC unit, also because it's a Renesas H8S family 16-bit single-chip microcomputer, which architecture is compliant with the data that we found earlier, and it is historically used as a system management controller. And it's, you know, pretty powerful. It has I2C bus interface, analog to digital converter. It has a serial interface. It can implement keyboard button control, which is compliant with being used as a keyboard controller, and metric scan, which is, however, unused by Apple. It is used in this fashion on Lenovo and ThinkPads, but not by Apple. And it has lots of generic I/O ports, which is compliant with having to control the different fans and so on. So, and according to the instruction set, the first thing that we see in the actual firmware image is compliant to a jump instruction, which actually makes sense that your firmware would start with a relative jump to somewhere in the code, bypassing all the different knobs that are here. So it makes perfect sense, and you can find the new development tools for it. So very quickly, because we're running out of time, you can disassemble very easily directly from the SMC file. So this is some, you know, conversion of the fact that you have the hex values, and it's not an actual binary, so it's like a text file. So, but once you've done that conversion to binary, then you can directly use the GNU development tool to disassemble the binary. And we see that, compliant to what we said before, the first instruction is a jump later in the code. So things start to make sense. And one other thing that you have to take care of, because these binary images, you know, things like EDA Pro, they don't really like them too much. You have to figure a few things around, is resolving the offset for the actual data that is present in the image, because you will see lots of things like these words being moved, and, you know, it actually turns out that these actually represent some values that are returned when you query an SMC key. So LMS is the motion sensor, so you can query and see if the motion sensor is on or off. No, sorry, that's an LED, it's not the motion sensor. So, and the way you can resolve these offsets, so you will see that in the binary at some point you have the data starting, and in this specific case, it will not start exactly at the same offset which is specifying in the code, but usually, depending on the architecture, everything can be shifted by a certain value. So here it's pretty straightforward to figure out that whenever you have an address like this, you have to apply an offset to it, and then you will find the responding value in the actual binary. So then you can either adjust your binary in order so that everything matches, or you instruct your disassembler and you tell him where actually this starts, which is not super easy, but you can do it. And also what you find in the binary are the actual SMC keys, which are being queried by user space. There's a table which defines them. And for instance, this key here, there's documentation which says that this key will give you the number of SMC keys, and we can see that we have the actual ASCII representation of the key name, which is what you pass in your query, and then we have an offset, which if we try to resolve that offset by applying the same shift that we had to apply before to finding where data is, we go to this value here. And this value gives 272, which is the exact value that you get when you query for that specific key from macOS. So this is making lots of progress. You know where the code is, you know where the data is, and you also understand roughly how the interaction between the user space and the firmware works in relation to the SMC keys table. And also one thing that you know, that you can do, because you know what the architecture it is, so you can look up the datasheet for it. And the datasheet will give you what the specific registers in memory will do. So by having that knowledge, it's straightforward to have code which, doesn't make too much sense and actually infer that this is an I2C operation. So this, for instance, is the code which talks to the battery for managing the battery operation, because the battery, and you might have heard of Charlie Miller's talk about Apple batteries, it talks through I2C to the system. And in order to do that, it goes through the SMC. So the SMC can control the battery. And this is one example of routine which actually respond to the SMC key and gives you an input back. So by modifying the firmware, you can obtain two things. You can, first of all, control all the different components which are attached to it, like the fans, the battery, and so on. And you also have a way of interacting with the user space. So as a user, you can talk to your own custom code of the SMC to either store data or do whatever custom functionality, and you can also get some feedback back, which as a tiny microcontroller on your laptop is a pretty nice example of the things that you can do. So running out of time, this is a standard disclaimer. This is an educational example only. So if you want to do it, don't break your Apple SMC, which is fairly easy to do. And yeah, so this was my example of final example of reverse engineering of an embedded system on a target which is very popular nowadays, which are Apple laptops. And do you have any questions, since we have 1 minute left? Yes, not from you. Right. So there are some tools that what they will do, they will automate the process of checking known CRC algorithms on your image, because one other thing that you have to figure out is what's the actual firmware space that the algorithm is computed against. Because if you have a header that you don't know it's a header which is not part of the checksum, then every time you try your checksum, that will fail. So there are some tools that will apply, 60 different algorithms, and they will start doing it at different offsets at the top and at the end, and they will try to understand and to exclude where the checksum is. Also because usually you have your checksum somewhere, like usually it's at the bottom, but that might not be always the case. And if you include that in your attempt, then you will always fail. So there are tools that automate that, but they do it against known algorithms, and you can find some that will automate the process of brute forcing the Rocksoft model to some extent, but there is no tool that will try to be creative and either detect your algorithm function within the code or to try and be creative in trying new algorithms. It's something which is difficult to do. Any other questions? Good. Thank you very much.